inside crystals. And why is it important? It's important because all properties of solids, materials, they are direct derivatives of how the atoms are arranged inside the solid. So not only is the identity of the atom important, but the arrangement of atoms is also important. For example, we all know about carbon. Carbon has a particular structure, and there are different kinds of allotropes of carbon. Diamond and graphite are two examples. So in diamond and graphite, the atoms are all carbon, 6 protons in each atom, but the arrangements are totally different, and this arrangement renders different properties to diamond versus graphite. And if you go into the realm of two-dimensional materials, two-dimensional solids, which is graphene, then the properties can be markedly different. So the arrangement of atoms, in addition to their identity, determines the properties of materials. And condensed matter physics is all about the properties of materials, properties of solids, be they the electrical properties, the magnetic properties, thermal properties, elastic properties. It's all about understanding matter. And most of the physics that people do in the laboratory is directly or indirectly revolving around this idea of condensed matter physics. So in the first couple of weeks, we're going to discuss how atoms are arranged within solids. Okay? So let's begin our foray into condensed matter physics by discussing in today's lecture the key elements and ideas of symmetry. Now, crystals are a unique class of materials. The arrangement of atoms inside crystals is periodic. It repeats itself. And when you have a periodic arrangement of objects, in our case atoms inside a material, then that network of atoms undergoes or obeys certain symmetry transformations. So we begin our discussion with symmetry in 2D. Okay. And the kinds of objects that we're going to deal with is, in order to understand crystalline matter, first of all we'll start looking at points. Then we'll look a little bit at polygons. We can also look at patterns. So we can make pictures of polygons, patterns, arrangements of points, and see what kind of symmetry operations do they obey. So what do I mean by points? In the language of crystallography, which is a science and art of studying crystals, arrangements of points, if they are periodic, they are called lattices. So a lattice is a three-dimensional repetitive network of points. Since we're beginning our discussion in 2D, let me draw different kinds of lattices. So one possible lattice is a square lattice. So this is a square lattice in which all these points are arranged in a square grid. Now these points are merely placeholders, they're only points. Okay, so they do not represent any atom or any structure, they're just points. So this is a two-dimensional square lattice. We can have a two-dimensional triangular lattice, a two-dimensional rectangular lattice, a hexagonal lattice, and so on. We can have different kinds of lattices. And these lattices have a certain functional form. If R is my position variable in space, then this two-dimensional network of points, which is a lattice, can be represented by a function L, stands for lattice. So this is what a lattice is. Remember, we're talking about 2D just to simplify our problem. Now, if you would like to build a crystal in 2D, then what we will do is we will attach a certain set of atoms, collection of atoms, with a lattice point, with every lattice point. Okay, so what the simplest thing we could do is just place an atom on each lattice point. And we get a square lattice. We already had a square lattice. Now we have a square arrangement of atoms superimposed on a square lattice. So now this becomes a two-dimensional crystal. We could also have another kind of repetitive unit that we place and attach to each atom. For example, we could have a pair of atoms. Say we have a pair of atoms, and if we define this to be our x-axis, this to be our y-axis, then we could define a pair of atoms. One atom, of course, is at the origin, and the other atom is at a distance a with respect to the origin at an angle of 45 degrees between x and y. So instead of attaching a single atom to a lattice point, we could attach this pair of atoms. So in that case, our structure will look something like this. Okay? So where the distance between these two atoms in this repetitive unit is A. So now on each point we have, on each point we now have a repetitive unit. So this unit that has been superimposed on each of these lattice points could be called, say, it could be called a motif or a basis. So this entire structure that is created is now called a lattice. So if you strip bare the points, if you strip bare the atoms from a structure, you're left with the lattice. A lattice doesn't have any structure associated with it. But then you attach a basis or a motif. Motif is a repetitive unit. You attach a motif to each lattice point to get a crystal structure. Okay? So this motif will also have a mathematical form. Suppose I call this mathematical form B. B stands for basis. B, this of course has some spatial variation, which means it's a Dirac delta function here at the origin and a Dirac delta function at this point. Okay? So this is my B. So now if I want to create the crystal structure, I would have to combine the lattice function with the basis function to create the entire crystal structure. What kind of mathematical operation would be needed to place each of these basis elements on to the lattice? Multiply? It's a close analog of multiplication. It's called convolution. So what I would need to do is I would take this lattice function and convolve this with the basis function. Overall, that will achieve the crystal structure, C. So this is the beginning of our discussion of crystals. We have a lattice, which is a two-dimensional or a three-dimensional arrangement of points, and on each point we associate one atom or a collection of atoms. We can even associate molecules with each lattice point. So we have a molecular crystal. Yes.
So lattice is something for an abstract thing to like kind of place our actual atoms, and it's not something physical itself.
Right. So the crystal structure is a convolution between the lattice, which is the grid of placeholders for the motifs, and the motifs are attached to each lattice point. They have each motif has the same functional relationship with the lattice point. So what you could do, instead of placing this motif on the crystal on the lattice point, you could place this motif such that the center between these atoms coincides with the lattice point. You'll get the same crystal structure again. So you can displace the entire structure by some unit in any direction, and you will still get the same crystal structure. This is the translational invariance inside this crystal structure. Yes, please. What's the convolution? So we're going to use convolution quite a bit in the first couple of weeks. So let me describe convolution. Does anyone know what convolution is?
सर वो जो सिग्नल्स के बीच में कन्वोल्यूशन होती है, आपने एक कर्नल के साथ आप सैंपल कर रहे होते हो और फिर इंटीग्रेट करते होते हैं.
Okay, so let me. So this is convolution. So convolution really means. So let me describe. First of all, let me describe what convolution looks like graphically. So if I have a function, say let's call this function L of R. Now I'm talking about a one-dimensional lattice. So there's only one kind of one-dimensional lattice. Since it has to be repetitive, the only one kind of one-dimensional lattice is that you have a point on regularly spaced intervals. So you have a Dirac delta function here, another Dirac delta function here, and so on. So this is our only example of a one-dimensional lattice, and this spacing, say, let's call it small a. So a one-dimensional lattice is represented by a train of Dirac delta functions. So this function LR would now be given by a Dirac delta function R minus NA. Okay, so this is a one-dimensional function. Everyone knows about Dirac delta functions? Okay, there could be some amplitude with this, but let's assume it's just a constant. Amplitude is 1. So now if I take another function, let's call this my basis function. This axis, by the way, is R in each of these graphs. Now, a basis function, let me assume my basis function to be a Gaussian function. Okay. So this function is some amplitude, say 1e minus r over delta, where delta is a measure of this width. And by delta, I assume it's much smaller than a. So now if I have two functions, one is a train of Dirac delta functions and the other is this Gaussian function, and I take the convolution of these functions. Now, just trying to describe what convolution physically and graphically means. Then what I would do is I would invert this function. Now, since it's a symmetric function, when I invert the function remains invariant. So if this were my mirror plane, if I invert this function, the function remains unchanged because it's a Gaussian function, it's a symmetric Gaussian function. So I invert this function, so instead of BR, I would be minus R. And then I take the inverted function, which in this particular case is the same as the original function, and sweep it from minus infinity to plus infinity. And when I sweep it, sweep means I translate it. And at each point I take a product between this function L and the function that has been inverted and is being swept. So if this function, so let me give you an example. So if I have taken this function, I have inverted it, I still have the same function, and my function lies here. So the original white function, the lattice function, is 0 everywhere. So if this function, which is being swept, lies to happen in an interval where the white function is 0, then I take the product of the two functions, I'll get 0. Only when this Gaussian function starts to, now since I'm sweeping this function, only when this Gaussian function hits a Dirac delta P will I get a non-zero value. And that non-zero value, according to the sampling theorem, is equal to the value of the Gaussian function at this point. So I keep on sweeping this function, I translate this function, and lo and behold, at the end, what I will have achieved is a new function, which is called the convolution of this lattice function and the basis function. And the new function, the convolution of the two functions, looks like the following. R. These are the locations of my Dirac delta functions in the original function, and I'll be left with this. Okay? So do keep in mind that if I have a Dirac delta function, at some R naught, and I multiply this with another function and I integrate over R, what's the result of this integral? B at R naught. Because this Dirac delta function is non-zero when R equals R naught, so it will only pick up that value of B which exists at R naught. This is called the sampling theorem. This is the sampling theorem. I am sampling this function at a particular value of R. So I use this property to achieve this result. I am sweeping the Gaussian function. This is like a comb, and this comb is filtering the function that is being swept, and it's picking up points on this Gaussian function one by one. It's most of the time it's 0, but when this Gaussian function hits the non-zero part of the lattice function, it picks up a non-zero value. So the impact of convolution is to take this motif and repeat it along the lattice function. And if you were to ask me how the mathematically the convolution function looks like, it looks like the following: L of R convolution with the basis function equals another function of R. Now how do I define this function? I take the original function L of R, I define a new variable R prime, I take B, I invert this original function minus R prime and add this running variable R, and I integrate over this running variable and do an integral over this R prime. So this is how you define it into different ways. Okay, so I integrate over R prime. This will give me a function of R, a new function of R. That new function of R is called the convolution of L and B. So any crystal structure is formed with a convolution of a basis function or a motive function with a lattice function. The lattice function tells you where to place the motive, and the convolution takes the motive and puts it on each point of the lattice. Yes, please.
सर उस केस के अंदर जो ग्रीन आपने गॉसियंस बनाए हैं वो सिर्फ उन पॉइंट्स के ऊपर एग्जिस्ट करेंगे, उनके आसपास तो नहीं होंगे ना?
नहीं, लेकिन अब ये वेरिएबल r. So whenever r changes, so this is our variable r prime, sorry. So whenever r prime changes by some amount, so it's changing, it becomes, at this point when this tail has some non-zero part, it becomes non-zero, it's still sweeping through this direct delta function. Non-zero, 0. So it's not at one point where this convolution is going to be non-zero. It's going to be over the entire width of this.
आप इंटीग्रेट किसी और वेरिएबल पे कर रहे हैं?
Yes, so this is how it works. Yes, please. So this is how the convolution is defined. So what you could also do is you could also define it in this fashion. You could put the minus beforehand as well, and it will give you the same result. So in fact, the motive has a center of inversion. Every crystal structure has a center of inversion. That's why it doesn't matter if you put a minus sign here or not. Then you'll put a plus sign over here. So because the translational invariance of the crystal, it doesn't matter. I put a minus sign, you invert it, because this is how the convolution is generally defined. Okay? It doesn't matter as well, because this r prime is going from minus infinity to plus infinity as well. So it's sweeping over everything. The convolution is defined by taking the inverse of one of the functions. Alright, so this is how a crystal is built. So there is a lattice, there is a basis or a motive, and the entire crystal structure follows from it. And when we try to discuss diffraction, when we shine light on a crystal or X-rays on a crystal, these ideas become really important. Okay. So I've defined a lattice as be it in 1D, 2D. We can also have lattices in 3 dimensions. Now let's talk a little bit about symmetry elements. In 2D, let's focus our attention on 2 dimensions before we move on to 3 dimensions. Any questions up to this point? So symmetry elements define how symmetry transformation takes place. And there are 3 kinds of symmetry elements. You can have a point, you can have an axis or a line, and you can have a plane. For example, if I were to, let me draw a pattern of polygons. So this is a pattern of polygons, and it's repetitive. And these polygons are in fact squares, and they're arranged on a square grid. So immediately by looking at this pattern of polygons, you can identify the lattice is a square lattice, and each motive is also a square. So now you're convolving between a square polygon and a square lattice. If you look at this crystal structure that has been created, this 2-dimensional crystal structure, even though it's very abstract, if I were to take this point here, any point inside this lattice, what I could do is I could draw a vector to a neighboring polygon. And associated with this vector, I draw another vector which is at the exact opposite. So this is a point. It has a certain object at a certain vector away, and at the exact opposite, it has the same object. So if there is some tiny little creature standing here and it's looking in a certain direction, at a certain distance it finds another creature at the exact diametrically opposite end, at the same distance it's finding exactly the same creature again. So this operation is a point operation. It's in fact similar to an inversion. Okay. So this is a point symmetry operation. I could also take this point here, or let's take any other point. Say, let's consider this point. If I take this point and draw an axis at this point, suppose this axis is pointing out of the plane of the paper, and I did a 360-degree rotation about this axis of rotation, about this axis, the entire pattern will remain unchanged. So I now have defined a one-fold axis of rotation, which is just a trivial rotation, but it's identified by an axis. I could also do a 180-degree rotation about this point, and still everything remains preserved. So I can also have a two-fold axis of rotation here. So I've defined an axis, a symmetry element which in this case is an axis. I cannot do a three-fold rotation about this point because then the symmetry will be lost. The new pattern that emerges after a 120-degree rotation about this point is not the same as the original. So there is no three-fold rotation here, but there is a one-fold axis of rotation which is just the trivial operation. There is a two-fold axis of rotation. There is also a four-fold axis of rotation. So all of these are symmetry elements which are associated with axes. Okay? I can also draw planes. So if I were to draw a plane like this, suppose it's vertical and it's a mirror plane, then this plane does exist inside this polygonal pattern. So now this mirror is a plane of symmetry. I can also draw this plane. I could also draw another plane. I could draw this plane. Multiple planes can exist. So symmetry elements are generally in two dimensions. They are classified. They could either be a point symmetry operation, they could be an axis of symmetry, they could be a plane of symmetry, and they have their own symbols. Okay. So now let's quickly move on to three dimensions. Any questions? So this science, as I've mentioned, of identifying symmetry in crystalline atoms is the science of crystallography. Crystallography came into existence soon after X-ray diffraction was invented, and say in the early part of the 20th century, when X-rays were used to probe crystal structures, and we started looking at the internal arrangement of atoms inside crystals. The need arose to classify these crystals and these symmetry operations, and what kind of symmetry transformations to different arrangements of atoms obey. So all of those materials were then classified into certain classes. Now each of these classes is a group, mathematical group. So I'm going to talk a little bit about these groups as well. Yes, please.
तो आपने जो X-ray diffraction का, that's what it's known as XRD.
XRD is X-ray diffraction, yes. So the X-ray diffraction is one tool to look at the internal structure of arrangement of atoms inside crystals. Alright, so let's move on to 3D, symmetry operations in 3D. since in ordinary cases our solids are three-dimensional. Okay, they're all three-dimensional. So in 3D, what kind of symmetry elements exist? Let's first look at the axes of the symmetry axes. We can have a symmetry operation which is just do nothing. Every crystal structure or lattice obeys this symmetry. You rotate it by 360 degrees about a certain point, it remains invariant. Okay? So this is symmetry operation in the international notation that crystallographers use is denoted by 1. Okay, so there are two notations that are used. One is called the international notation or the HN notation, Herman Manguin notation, which is a standard notation crystallographers use. And I'll later, sometimes it's convenient to use the other notation which I'll describe in a minute. So there is the one-fold rotation, which is just a trivial rotation. You can identify this as a point rotation or as an axis of rotation, doesn't matter. Then you have a two-fold rotation. And I'm putting these notations, these symmetry operations in slightly boldface. So you can have an axis of rotation about which a 180 degree rotation takes place, and the pattern or the lattice or the structure remains invariant. You could have a three-fold rotation, which is a rotation by 120 degrees. You could have a four-fold rotation, and you can have a six-fold rotation. So there are these 5 symmetry operations that can exist. And there are others as well in 2D. So there are 5 of these point operations or axis operations. There is another. So let me first kind of exemplify this. Let's consider this 4. In this structure, this point is a 4-fold axis of rotation. This point is a 4-fold axis of rotation. This point is a 4-fold axis of rotation. Neither of these points is a 6-fold or a 3-fold axis of rotation. It's also a 2-fold axis of rotation. Okay. Every point is a 1-fold axis of rotation. Correct? So we have these 5 symmetry operations in 2D. Yes.
So by 2-fold you mean rotation by 180 degrees, and by 3-fold matlab 360
rotation by 120 degrees.
Right.
There are 2 additional rotations that are allowed. 2 different additional operations that are allowed. You can have 1 bar. Now what does 1 bar mean? 1 bar means exactly this thing that I described earlier, probably here. Oh, this. If I have an object at R, there is also an identical object at minus R. So this is an inversion. This is a 1-fold axial rotation, 2-fold axial rotation, 3-fold, 4-fold, 6-fold axial rotation. You can also have a point of inversion or a center of inversion. This is called a center of inversion, an inversion operation. Okay, let me list down all the symmetry operations first that are valid in 2D. So 1, 2, 3, 4, 6, 1 bar, which is an inversion operation. I'll explain what it means. You can also have 2 bar.
These are not bold.
bold is a 2-bar rotation followed by an inversion. So 2-bar means a 2-fold rotation followed by an inversion. Whenever you have a bar, it means an inversion. I've explained inversion, but let me give you examples of this. And this 2-bar operation, I'll show what it means in a minute, and it's very interesting. Square lattice, square motifs. Here, I have a 2-fold axis of rotation. Okay. So a 2-fold axis of rotation coming out of the plane of the paper exists. So there is a 2 symmetry element here. There is also a 4 symmetry element here. Correct? There is also a 1 symmetry of element here, but there doesn't exist a 3-fold axis of rotation or a 6-fold axis of rotation. You cannot have 5-fold axis of rotation, by the way, because just imagine that you have pentagons. Those pentagons cannot fully fill a 2-dimensional plane without leaving any gaps. So you cannot have a lattice is an infinitely repetitive unit. You cannot have a lattice which has 5-dimensional symmetry. Okay, because then you cannot completely fill the entire space. Okay, so 5-fold axis of rotation don't exist. So there is a 1-fold axis of rotation, there is a 2-fold axis of rotation, there is a 4-fold axis of rotation. There is also a 1-bar center of inversion here. Because 1 bar means that if I were to take a vector from this point in a certain direction, there is exactly the same thing on the opposite side at the same distance.
But sir, it will depend on the origin point जो हमने choose किया हुआ है.
So exactly. So you do not have a point here. It's at this point which has all of these symmetry elements. All of these axes pass through this point. Okay. So there is a 1-fold axis of rotation, a 2-fold, 4-fold, and a center of inversion here as well. Now, what about 2-bar? What is 2-bar? 2-bar means you do a 180-degree rotation and follow it by an inversion. So if I take this polygonal pattern and I rotate this by 180 degrees, rotate the entire thing by 180 degrees, I already have 2-fold axis as an axis of rotation, so I get the same point. But then, if I follow it by inversion, then it still gives me the same polygonal pattern. So, a 2-bar also exists over here. Now, this 2-bar really means a mirror plane. So, a mirror plane exists. So, let me explain this in another fashion. Let me draw a diagram which is commonly used in crystallography, which is called a stereographic projection, a stereo picture. Okay, this is a stereogram. It's just a circle, and I draw an object here. Some object. Now, if I take this object and I do an operation 1, what is this object transformed to? This is my axis of rotation. I do an operation 1. What is this object transformed to? It doesn't change, it remains there. So the action of 1 is that nothing happens. Okay. Now let me draw another stereogram. same object and I do this point now becomes a two-fold axis of rotation. Now a two-fold axis of rotation also has certain symbol. It's like an oval shape, so this shows that this point is a two-fold axis of rotation. So what happens if I do a two-fold axis of rotation? Where does this object go? Banana. किधर जाएगा ये point? जल्दी जल्दी. इतना इसके पास जाएगा. So this is what a two-fold axis of rotation does. Okay. Now three-fold axis of rotation. This point goes here. So now this is a three-fold axis of rotation. It can be represented. This axis of rotation can be represented by a triangle. A four-fold axis of rotation would take this point here. By the way, if you want to complete this picture for a three-fold axis of rotation, this point after another three-fold axis of rotation will land here. And after another three-fold axis of rotation will land here. As a result of a four-fold axis of rotation, which is represented by this colored square inside the center, these 4 points are generated from a single point. So whenever you have an arrangement of points in this fashion, it has a four-fold axis of rotation. Likewise, we can have a six-fold axis of rotation. Say, this is a six-fold axis of rotation. So, as a result of a six-fold axis of rotation, this stereogram is generated. And all of these 6 objects are equivalent. They are relatable to a six-fold rotation. They are equivalent. Now consider one bar. Okay? One bar means suppose I have an object here. And what I would like to do is, let's first consider 2 bar. Let's consider 2 bar. Okay? That's easy. Let's consider. So 2 bar means a two-fold rotation followed by an inversion operation. This is what 2 bar means. So I do a 180-degree rotation, which is this stereogram over here. But then I would like to do an inversion operation. Okay, so what does that inversion operation do? So if this is my two-fold axis of rotation with a bar which has this kind of symbol, so I do a two-fold axis of rotation, then I want to invert about this point. So this point, when inverted, comes back over here. Okay, now I want to show you how this works, but let me first show you at this point what a 1 bar does. An object. This is my point of inversion, a 1 bar point, an inversion point, the center of inversion. What this does is it creates a point here on the opposite side, but then this point also has to become the enantiomer of this point. Okay, let me explain what this really is. I have my 2 hands. These are my 2 hands. Is there any symmetry operation that relates these 2 hands?
180 degrees.
No, I cannot, if I rotate this by 180 degrees, I mean, I do not get the same.
इसरा तो इसरा mirror image बन जाता है.
Mirror image तो है, लेकिन mirror image is not the same as 180 degrees. So juxtapose your hands like this, right? If my hands are like this, and I connect equivalent points on my 10 fingers, 5 fingers here, 5 fingers here. If I connect my equivalent points on the 5 fingers and connect them by straight lines, all of those lines will pass to a single point. That single point is the center of symmetry. It's a center of inversion. Okay, and these two hands, they are the mirror images of one another. So in this case, I have my palm facing towards me, and here my palm is facing towards you. So they are opposites. They are opposites of one another. If I have a left-handed object here, it will appear as a right-handed object in the mirror plane. So these two objects that are not 180 degree rotation counterparts of one another, but they are connected by a center of inversion. They are called enantiomers of one another. A left-handed molecule is an enantiomer of a right-handed molecule. This is a right hand and left hand, they are enantiomers of one another. Okay? So enantiomers, if I have an object here, its enantiomer is represented by the same object where there's a comma inside it. Okay? So one center of inversion is represented by an object followed by its inverted image. Inverted image means the same object but it's an entire. Okay? So this is a center of inversion operation. Now if I would like to do a two-fold axis of rotation followed by a center of inversion, a two-fold axis of rotation will land this object over here, but then I want to invert it across this point. So it will coincide with the original position of the object. So this means that the object and its enantiomer are coincident. So I break this point into two and put a comma in one half of it. So a two-bar operation has a stereographic projection like this. Okay, so now I'm done with the symmetry operations in 2D. So these are all the symmetry operations in 2D. In 3D, I have additional symmetry operations as well. So, ये कितना भी 1 2 3 4 5 6 So these 7 symmetry operations, they are valid in 2D. An arrangement of points, which is a lattice, an arrangement of polygons, an arrangement of patterns will have one of these 7 symmetry elements or more. Every of these objects will have this trivial operation as a symmetry operation. Okay. So there are 7 symmetry operations associated with two-dimensional patterns, planes, and polygons. In 3D, we have additional symmetry operations, 3 of them. So in 3D, we have all 7 of them. 1, 2, 3, 4, 6, 1 bar, 2 bar. By the way, this 2 bar, if you look at this 2 bar, it's something really interesting. This 2 bar is like a mirror plane, which is horizontal. And I'll explain this later. Okay. So these are all my symmetry operations in 2D. In 3D, we have additional symmetry operations which are 3 bar, 4 bar, and 6 bar. 3 bar means a 3-fold rotation followed by a center of inversion. 4 bar means 4-fold rotation followed by an inversion. 6 bar means 6-fold rotation followed by an inversion.
So the order matters. The order matters of symmetry operations. If I write the inverted first, then rotation, will it change?
So there are two parts, two answers to this question. So if I have a 3 bar operation, which means that 3 bar operation is a certain symmetry operation. In this particular case, the order doesn't matter. But 3 bar is like a group. So when you have 3 bar, it forms a group of symmetry operations. And within that group, that's a non-abelian group, which means that the order does matter if you look at all the symmetry operations of that group. Okay? So these 7 operations belong to 2D. Whereas in realistic crystals, real structures, you have these 10 symmetry operations. So in 3D you have these 10 operations. And all of these 10 operations, since all of these operations involve a point, the axis of rotation also goes through a point. Even though it's a line operation, but it passes through a point. All 10 of these operations are called point operations. They're called point operations. Now let me give you an example of 4 bar. If I draw a 3-dimensional cube, this is a cube, and my lattice comprises the vertices of this cube. So this is a cube. Can you identify 4-fold axes of rotation in this cube? This is a lattice. Is there any 4-fold axis of rotation? Right. There are 3 mutually intersecting 4-fold axis of rotation. One through this middle, one through this side, and one coming out, right? That's not a 4-fold axis of rotation. So you have 3 mutually orthogonal 4-fold axis of rotation. Which means that if I were to properly label these axes of rotation, I would put a square here. So it's a 4-fold axis of rotation. Right? So I have 3, 4 axes. 3, 4 axes. Okay, that's why I put this 4, which is a symmetry operation in bold. 3, 4 axes, or 3 4-fold axes. And these are 4-fold axes because if I, for example, take this axis, which is vertical, and I rotate the entire thing by 90 degrees, the cube remains invariant. Now, if this point at the center, is this also a center of inversion? It is. So if I consider this point A and I take its inverted image about this center of inversion, which means I do a 1 bar operation on A. I take this A and do a 1 bar operation on A. I land here at this point B. And there is a point here, an identical point here. So this is indeed a center of inversion for the entire cube, which has lattice points at its edges, at its vertices. Sorry. So this means that we have 3 4-fold axes. We also have a 1 bar at the center of this cube, at center of inversion. This also means that if I were to do a 4-fold axis of rotation and follow it by a 1 bar operation, so will keep this structure invariant. Because if I were to do a 4-fold rotation, this point B will go to A and A will then go to B prime. So corresponding to a 4-fold operation followed by an inversion on point B lands me here. So I move the entire thing by 90 degrees about this axis and then do an inversion, I'll get the same structure back. So this point is a 1 center of inversion, and this axis is not only a 4-fold axis, it's also a 4-bar axis. So I also have 3 4-bar axes. It's not only a 4-fold axis of rotation, it's also a roto-inversion axis. These are called roto-inversion axes because these are rotations followed by inversions, or inversions followed by rotations. Okay? So in 3D we also have these 3 possible roto-inversion axes. These are roto-inversion axes. Got it? So not only is this a 4-fold axis rotation, it's also a 4-fold roto-inversion axis, which probably has this symbol. It's a 4-bar roto-inversion axis as well. So the 4-fold axis rotation and the 4-bar roto-inversion axis coincide. So does this structure also have a 2-fold axis rotation? Yes, it does. In fact, these lines also are 2-fold axis rotation. Is this line also a 2-bar? Is this also a roto-inversion axis like this? 2-bar, yes. So if I take this point and do a 180 degree rotation and end up here, this point will then be inverted to this point. So as a result of a 2-bar operation, this B will be transformed to C. This point will be transformed here. A will go here. This point will be transformed and it will go here. This point will be transformed and it will go here. So these axes are also 2-bar axes. And we know that this 2-bar axis is the same as a mirror plane, because this 2-bar operation, what the 2-bar operation is doing is that taking these 4 points and taking the mirror image with a mirror plane that lies in the exact center of this cube. So this 2-bar operation is exactly equal to a mirror operation, M. So this 2-bar operation can also be identified as a mirror plane. We can also have 6-bar operations, 4-bar operations. Take a hexagon and you will notice that it has a 3-fold axis rotation, it also has a 6-fold axis rotation, as well as 3-bar, 6-bar. If I were to take the edge of this cube, is the edge a 2-fold axis rotation? Yes. It's also a 4-fold axis rotation. So there are additional 3 axes that lie along the edges, which are axes of rotation: 2-fold, 3-fold, 4-fold, and so on. So this structure that I have drawn has a large number of symmetry operations associated with it. And what I'm going to show in the next class is that different symmetry operations can clamp together, they can be lumped together and form classes of symmetry. And in 3D, only 32 such classes exist. And those are called the point groups. So the next lecture, we're going to study the 32 point groups for crystals. By the way, I also kind of promised that I'll tell you a little bit about the alternative nomenclature. So these symbols that I've drawn here correspond to the HN notation, the international notation. The old notation would present this one as C1, a cyclic operation, order 1, cyclic operation, order 2, C3, C4, C6. Okay, this would be represented by as an improper inversion S1, this as S2 or M, this as S3, S4 and S6. So this is the old notation, or material scientists actually would like to use this old notation. It's called the Schoenflies notation. This is called C's because they are cyclic operations. Right? These are just like if you have a group which comprises 3 elements, 1, iota, and -1. They form a cyclic group. Okay, with respect to multiplication. That cyclic group is actually isomorphic to C3. So all of these symmetry operations, these 10 different kinds of symmetry operations in 3D can be lumped together in 32 distinct ways. Those ways correspond to 32 groups, mathematical groups. They are called point groups. Those 32 point groups kind of cover all the possible macroscopic crystal structures. I mean, there are additional groups possible because of translation, because if you ignore all the translations of atoms and only consider point operations, 32 groups exist. They call the 32 point groups. And these 32 point groups also control the outward appearance of crystals. And they control all the macroscopic properties. Other additional elements which are translational symmetry elements do not control physical properties. They are only controlled by which group does a material belong to. So the next lecture will develop the 32 point groups. Okay, so I'm going to upload material relevant to all of this on the website. Anamta is the TA.